Hello, welcome to Math with Beth. And today we're going to look at related rates. And we're going to use implicit differentiation to do the related rates. So let's take a look. Okay, what is a related rate? It is any equation with two or more rates expressed as derivatives. So in this example, this is a rate because it's the rate that y is changing with respect to t. And this is a rate because it's the rate that x is changing with respect to t. So let's do an example. So this is just a random equation, but then we're going to do a word problem where it will make a little more sense. If I wanted to find dy dt, that's my hint that I need to do implicit differentiation because it's asking me to find the derivative of y with respect to t. And we don't even have t's in this problem. So we're always going to have that extra step of doing the dy dt or the dx dt. So we're going to have it for both. And here's another hint because it gives me a value for dx dt, which I don't have right now. So I'm going to have to find that by taking the entire derivative of both sides. So the derivative of y is just going to be dy dt, because basically it's 1 times dy dt, so you don't need to write the 1. The derivative of 3 times the square root of x, since that's really the same as 3 times x to the 1/2. I'm going to use the power rule where I multiply the 1/2 times the 3. And then I subtract 1 from the 1/2. But then again, since I'm doing it with respect to t, I again have that extra step of saying dx dt. So anytime you're taking a derivative with respect to a different letter, you'll always have that extra step. So the only time we haven't had that so far is when we've been doing normal derivatives with respect to x. So anytime we did something with the x, we didn't have to do that extra step. But now we do. So here's our equation. But now it wants us to find this specifically when x is 9 and dx dt is -4. So that just means we can now plug those in. So dy dt, which is what they wanted us to find, so we found it, is this, but now plugging in 9 for the x and -4 for the dx dt gives us 3/2 times, this is really the square root of 9 on the bottom, so that's really 3. So since this is 3, we really can reduce the 3 and the 3. So we really end up with -4 on top, 2 on the bottom. So in other words, -2. So that is the rate the y is changing with respect to t. But since this isn't an actual word problem, that doesn't mean too much. So let's do a word problem and see if this makes a little more sense. A colony of bacteria in a petri dish forms a circle whose radius is increasing by 0.7 millimeters per minute. So increasing by this much means this is one of the rates. Okay, and specifically it's talking about how the radius is changing with respect to time because it's saying per minute. So this is really dr dt. Does that make sense? It's the rate that the radius is changing with respect to time. Find the rate of change of the colony's area. So what they want us to find is dA dt. So that's what we're going to try to find. At the moment, its radius is 12. So this is similar to the last one where we're trying to find a certain rate and they've given us some of the numbers we're going to be able to plug in. It's just the only problem is they did not give us an equation to start with. But we should know it because they're talking about a circle and they're talking about its area. So you should hopefully remember that the formula for the area of a circle is pi r squared. So if we now need to involve all of these rates, we basically need to take the derivative of both sides with respect to t. So a will become dA dt. Since pi is just a constant number, the pi will stay, but r squared would become 2r to the first power. But then again, we have to add that extra step of dr dt. So now we can plug in what they've given us, which is pi we know, 2 we know, the radius they said is 12, and the dr dt they basically said was 0.7. So if you multiply that all together, which I did earlier, you would get about 52.78. So what units would this be? Since this is the rate that the area is changing, and we're talking in terms of millimeters, the area is going to be millimeters squared. But this isn't just the area. This is the rate the area is changing. So it's not just millimeters squared, it's millimeters squared per minute. So that is how to do it with an actual word problem. And we're going to do that one more time with a word problem involving cost and revenue. So for Bob's Landscaping, the total revenue and total cost in dollars for yard maintenance of X homes, so the X is going to stand for the amount of homes, is given by, here's our equation for revenue, and here is our equation for cost. So what do they want us to find? Suppose Bob's is adding 10 homes per week at the moment the 400th customer is signed. So it's adding 10 homes per week. So this is a rate, and it's the rate that has to do with the homes, which is X. So that is going to be our dx dt once we get it. And the fact that it's the moment the 400th customer is signed, even though they say customer, that's the same thing as thinking about 400 homes. So that is really our X, right? If we have 400 customers, we have 400 homes. So at that moment, what is the rate of change of? And then we're going to do all these different things. So if they want the rate of change of the total revenue, I'm going to use this revenue equation. So the derivative of R of X, you don't really need the X. You can just make it a little simpler and say the derivative of that, if we're doing everything in respect to T, would be dr dt. The derivative of this would be 1,000, but again, because of the X, you have to add that extra step. And same thing over here. The derivative normally of X squared would be 2X, but we have to add that extra step. So there's our equation. But now they want us to do it with the actual numbers they gave us. So now we can plug in 10 for dx dt and 400 for X. If you do that, you will get 2,000. So remember, this is money we're talking about. So this is the rate the money is changing when we've had our 400th customer. And it's changing $2,000 per, let's see what type of time we're talking about, per week. So that is the rate the revenue is changing at this time. So now let's do the same thing for cost. So if you want to pause it here, maybe try this one yourself. That would be a good idea. So do the derivative of this in terms of T. So the C becomes dc dt. 3,000 becomes 0, so I don't need to write that. And 20x is just 20, but because it's this type of problem, we have to add that extra dx dt. Now again, we can plug in dx dt, which they told us is 10 at this time. So the answer to this one would be 200 per week. So that's not too bad because we obviously want the revenue to be larger than the cost. So that's good. So for total profit, we can find the profit equation by doing revenue minus cost and then do everything we just did, or we can take a shortcut. Since we've already done this with the revenue and the cost, we can just subtract those answers instead. So we can find our answer of dr dt and subtract the answer we found when we did dc dt. So in other words, 2,000 minus 200. So that would be how much the total profit is changing at the time when we have our 400th customer. So it really isn't that bad once you get used to this extra step that's involved anytime you're doing a derivative in respect to a different letter than you have. And for most of these word problems, it's going to be with respect to t. So again, feel free to let me know if you have any questions. Just give me a comment and I will answer it as fast as I can. Thank you.